Hey guys, today we're going to talk about how astronomers measure the stars, some of the things that they look for. Um, we already talked about stellar parallax a little bit, and it's basically how we judge distance, is one of the ways we judge distance anyway, um, to get relative distance to stars based on how much we move. The nearest star to Earth is, or sorry, nearest star to the Sun is Proxima Centauri, which is a member of a three-star system, which is called the Alpha Centauri complex. If you were to model distances and imagine the sun is a marble, then think of how long a meter stick is. The Earth would basically be a grain of sand about a meter away. Then the next nearest star is about 270 kilometers away. So think like New York City. Just to give you an idea of just how much space there is in between things. And then the solar system extends about 50 meters from the sun. This is just a map of the 30 closest stars to the sun. The next nearest neighbor is Barnard Star, which looks, and you can see in the arrows here, looks as we go around the sun as though it moves the most. That's what they call the proper motion due to parallax. We're going to skip that. As far as naming stars goes, we started off naming the brightest stars, and Procyon is an example of that. Starting in 1604, stars within a constellation were ranked in order of brightness. So, like Alpha Centauri, so Alpha would have been the brightest star in the Centauri constellation. In the early 18th century, stars were numbered west to east in a constellation. Example of that would be 61 Cygni. Then, as more and more stars were discovered, we had to come up with more and more different naming schemes. Now we basically just label them by their celestial coordinates. Luminosity, or absolute brightness, is the measure of the total power radiated by a star, whereas the apparent brightness is how bright a star appears when viewed from Earth, which depends on the absolute brightness but also the distance. Therefore, two stars that appear equally bright may be a closer but dimmer star and a farther brighter star. And down here it shows, just showing you, hey, those could be two very different stars, but that's kind of what we see here from Earth. The apparent luminosity is measured using a magnitude scale, which is related to our perception. It is logarithmic. A change of 5 in magnitude corresponds to a change of 100 in apparent brightness. So it is also inverted. Therefore, you see down at the bottom, the negative values are higher. So the highest negative value is the sun. Then after that would be the full moon. Then the next brightest thing that you see in the sky is Venus. You guys, I'm sure, have all seen Venus. Most people see it and think that it's just another star. But so you get from that scale, you kind of get an idea of what we can see. And the reason why the star's apparent magnitude changes is because if you look at the diagram here, the shows the light source. Well, at, like, we'll say this is 1 astronomical unit. At 1 astronomical unit, that light takes up 1 square, whereas at 2 astronomical units, that light would take up 4 squares. And at 3 astronomical units, it would take up 9 squares. So the same amount of light is being spread over a much larger area. We also look at stellar temperature. So I like this picture down here on the bottom right, just because it really gives you an idea of all the different colors the stars have. I know when we look just with our eyes, we don't get that sense. So red stars are relatively cool, while blue stars tend to be hotter. The radiation from stars is what we call black body radiation. As the black body curve is not symmetric, observations at 2 wavelengths are not enough to define the temperature. And we break the stellar spectra into 7 classes, although there are a couple more, but these are the main ones. So from highest to lowest, it's O, B, A, F, G, K, M. And notice going from top to bottom, these are the spectra for different types of stars. So here you can look at what you would kind of expect to see for a spectra for all of these different types of stars. This might be helpful with one of the assignments that you're going to be doing. So kind of keep this in the back of your mind to take a look at this slide when you look at the spectroscopy assignment. This also could be helpful for that. This is spectral class, temperature, and then what type of absorption lines we tend to see in those. We're going to skip that. One of the reasons I like to show this slide is because this is Betelgeuse, which is one of the largest red supergiants that's closest to us. It's the upper left shoulder of Orion. And down at the bottom here, this says the size of Earth's orbit. Now notice, this isn't the size of the sun. This is the size of our whole orbit. So from one side to the other. So this is 2 astronomical units in distance and takes up about that much. So Betelgeuse is absolutely huge in comparison to the sun. Stellar radii vary very widely. So in other words, stars can be absolutely huge. Antares is 500 times the radius of the sun, whereas you get down to things that are 0.08 the radius of the sun. So very large differences in just how big stars are. This is what we call the HR diagram. This is really important because this is kind of where we're going with this. You guys are going to have an assignment on this. So the HR diagram plots stellar luminosity against surface temperature. So luminosity goes on the left, surface temperature goes on the bottom. And notice that along with surface temperature, it also has the spectral class and the color. So the bluer stars are over here, and those are the O class stars. And the redder stars are over here, and those are the M class stars. Notice that the sun is pretty much right in the middle region here. So this is an HR diagram of the 80 closest stars to the sun. This is what we call the main sequence. We're going to talk more about the main sequence later on when we talk about life cycle of the star. This is the white dwarf region down here. So if you look at the 80 closest stars to the sun, they tend to be stars that are smaller and relatively cooler. And we have some white dwarfs. The 100 brightest stars looks very different. Okay, so now you see the upper part of the main sequence is filled in. Then you have some blue giants up here and some red giants and red supergiants up in this region. So just to give you an idea of what this looks like, when we look at the 20,000 stars, this is what the HR diagram tends to look like. About 90% of the stars lie on the main sequence. That's right here. And 9% are red giant, red supergiants. And then about 1% are the white dwarfs and stuff. One of the reasons, and we'll talk more about this later, is these guys haven't had a chance to go through their life cycle to get down here. That's why this is kind of a small percentage right now. Let's see. We're going to skip over some of this. That's not super important for you guys. This is just talking about how we find exoplanets or eclipsing binaries. So changes in the brightness and luminosity, you can see as one thing goes in front of the other, you get dips in the brightness over here. I think that's about it. So we'll stop it there.